Hey everybody, it's me again with your pre-cal video on 6.3. What I wanted to mention to begin with is these type problems with a negative angle relate to the odd and even identities. You have sine of negative x is negative sine x, which basically means if you have a backwards angle, it's going to be negative for sine because that's downstairs. And same thing for cosecant because those are a pair. Cosine would be positive, and so that actually works out where those two are both positive for cosine and secant despite having a negative angle because the values are the same. Just like when we talked about square root of 3 over 2 comma something, like a half. Over here it'd be square root of 3 over 2 negative a half. And so you can see the cosine of negative x is the same as cosine x, but sine of negative x is not. It's negative sine x. So that's just a little example. And for tangent, it's the opposite sign because remember, it's positive in these quadrants but negative in those. So that is what we're getting at. Now, where did I find that paper? Right on the back side of your unit circle. You have your unit circle, flip it over. There's your reciprocal identities, which we've been using a little bit, and the quotient ones. We haven't gotten to the Pythagorean identities later. Or yeah, that's another chapter, and this is what I'm talking about now. Everything else is later. But that's where I'm getting the reciprocal, the negative parts from the negative angle. So when I had mentioned if it's up here it's positive, if it's down here it's negative, that's where I got that from. Because for tangent, it'd be negative. Now, I did a little bit more research and I saw how they related this in the Math Excel view and example. So what they first did is they took the right side, which is tangent 29 pi fourths, and they wrote it, and sorry that's a little messy, but that's 14ths. Tan 29 pi over 14. And what you would have to do is break it up into 2 pi plus 1 pi 14ths, because 28 pi over 14 is equivalent to 2 pi, which is one complete loop around. It's like one revolution. And now if it is just going back to where it was, because it's coterminal, then we don't even use the 2 pi part. So we just have tan of pi over 14 for that part. Now for the cotan part, you use this part where if it's cotan of a negative angle, then it's negative cotan of that angle. And so cotan of negative pi 14ths is equal to negative cotan of pi 14ths. Now the next step is you relate tan and cotan like this. And so I'm going to rewrite cotan in terms of tan. So it's 1 over tan pi 14ths. So those are the first two steps. And now going back to this, we had cotan first, which is this one, and we had tan next, which was this one. The order doesn't really matter when you're multiplying, but notice if you have tan of pi 14ths here and tan of pi 14ths in your denominator, they would cancel, and so you're left with negative 1. Now on these next couple of questions, including that one, you might just want to try using your calculator, even though it says do not use a calculator, because I'm not going to take up your calculator in the middle of the test. And I'm not going to just test you on a couple of things. So you might just want to type that in like we said in the other video and use radians. Now, if you do this one on the calculator, use degrees. As a reminder about how you switch them around, from your home screen, you go to calculate, and here you can see I'm in radians because it's rad. And if I click up here like this, that puts me in degrees. So then I could say sine. So I press the trig button, which is right there next to the equal. So there, and then sine -50. Now, since I'm in degree mode, I don't really need the symbol, but I'll still put it just so you see where it is. You press the little pi button, which brings up a menu, and the degree symbol is right there. So sine -50 degrees, then go to the right, and then you're dividing by cosine of 410 degrees, and you're adding tan 230 degrees. So when you do all that, you get 0. So if you do that on the calculator, you get your answer. Now, what they were hoping y'all would learn is that sometimes the angles are related. Like this one could be thought of as, okay, you got 50. How can we get 50? We could get 50 from doing, hold on, let me pause this for a second. Okay, I thought of what I was going to say. What we start with is if this is 410, then subtract 360 to find the coterminal, which is 50. Remember that coterminal means it loops around all the way 360 degrees, and then it's 50 more. So that's why 410 and 50 are related. Now, we are just going to keep this as sine of -50 at the moment. And then this would change to cosine of 50. And then this would be tan. Let's see, 230 minus 180 is also 50. So on 230 degrees, that'd be in this quadrant, like you go around to right there. And so the reference angle from the x-axis would be 50. So let's rewrite this. Since this one and this one would have the same value, we just put tan 50. Now, when you go back to what we were talking about earlier about sine of -50, sine of -50 would be equivalent to negative sine of 50. So we have negative sine 50 over cosine 50, and then we're saying plus tan 50. Now sine over cosine is really tangent, so we get negative tan 50 plus tan 50, which is 0. So that's how the math really works out and what teachers are really going to want you to do. But if you want to use your calculator and see how it works out, you can. It's just if you get a funny decimal, then you're going to have to figure out the other way to do it, like this. But if you end up getting 0, -1, or 1, then I just use the calculator to get it. Okay, so there's number 13. Now number 14, what is the domain of the secant function? So to get that, we go to this page, which is all about sine and cosine. You see their domain and range. You flip it to where it says other circular functions. Here they're talking about tan and cotan. And then here they're talking about secant and cosecant. So it tells you in the notes that secant is undefined at pi halves, 3 pi halves, and at those negative places, because that's where the vertical asymptotes are. And so that's where it's undefined in your domain. And then it says both of them have range from -infinity, like as low as you want, up to -1. And then it is defined from 1 to infinity, just not in between. So remember how that works is if you have one of them, I guess in this case we're talking about secant. So the partner of secant is cosine. So for our cosine graph, it looks like that. And so for our secant graph, it's going to look like that and like that, and then back to that, you know. So this is your secant, and this is your cosine. Now, what they're showing you is just a very limited part of it, which is your 0 to 2 pi, because your period is 2 pi. But here it kind of just looks like that. Now, if I were to really graph it and zoom out a little bit, or use the regular trig window, you can see it's not really just half. That's what I'm trying to show you. If we press the trig button and go to secant, now, by the way, I know I said this before one time, but if you're trying to graph trig, you have to be in radians. So let me change this back. Secant x, and I'm in radians. So it's not really just like half of a parabola. It's like a parabola over and over again. And some of them are up, some of them are down. But if we go to the window we talked about on the other video, that's the trig window, which is number 8, and it looks like that, where it does show just half here and half there. But if you just want to show exactly what they're talking about, you double click there, press 0, and there you go. So that's why that looks like that. Okay, so getting back to what our actual question was, it's all real numbers except odd multiples of pi halves, because you have these vertical asymptotes at pi halves, 3 pi halves. The next one is 3 pi. The next one is 5 pi halves, and it would continue at odd numbers in the numerator. So these are odd numbers in the numerator. Like, I guess I'll back up a little bit. -3 pi halves, -pi halves, pi halves, 3 pi halves, and 5 pi halves. So the key word is odd, because that's like 1, 3, 5, so forth. It wouldn't be integer multiples, because that'd be plus and minus whole numbers and relating to 180. And it wouldn't be the same thing, like plus and minus whole numbers of this, because then that would be like not only negative 3 pi halves, but negative 2 pi halves, which is really negative pi. And you don't really have an asymptote there. I guess I could keep going. Negative pi halves, 0, pi halves, pi, etc. So you can see that at pi we actually have a value. So there's not an asymptote or a hole right there. So that's that. And it would also not be all real numbers because that'd be cosine or sine. Okay, so now for tangent, again, use your notes. Tangent is undefined right there, actually at the same place secant is undefined. So notice both of these say negative pi halves, 3 pi halves, etc. So odd multiples of pi halves. Now, if you have a different trig function, your answers may be different. So secant, secant and tangent have the same asymptotes. At pi halves, odd multiples, and cosecant and cotangent have the same asymptotes at this is where it's negative pi, 0, pi. So at whole number, or even number is what I should say. What's the best way to say that? 0, 1, 2, yeah, at whole number. Whole number or multiples. So that'd be back to like integer multiples of pi or 180. Integer multiples of pi or 180 degrees. Now, as y'all know, on your particular homework question, they could change, the trig function, they could change the order of these. Of course, they change the numbers and all kinds of things. But the wording of the question would be the same, except for the actual trig function and, what the answer is. For your next one, we want the range of cotan. So the range is everything, negative infinity to positive infinity. So that means all real numbers. So it's basically low to high. And the graph itself looks like that. Whoops, I guess I have it that way, but it should be, I can make that a little bit better. I should have done it like this. That's the graph, not that one. It's close, but not exact. So that's the graph of cotan. And so think about the range this way. Because it's the y values. Now we want the range of tangent, which would actually be the same thing. Tangent goes through the origin and kind of looks like x cubed a little bit. It's like x cubed repeated. So, for example, tan x, like that. And if I go to x to the third, it's kind of like that. Let me go back to a standard window for what I'm doing now. So there's x cubed, but then the blue one, which is the trig one, is over and over again, you know, in front and behind. So again, yeah, the blue one, blue is the trig tan x, and the red one is the x cubed. So they are pretty similar, just not exact. And then it repeats. Okay, so the whole idea is use this reference sheet, you know, for sine and cosine for your domain and range, because those are all -1 to 1 for your range, and all reals for your domain. And then there's those two, and here's these two. Okay. One last one. Now, is the tangent function even, odd, or neither? Now, a long time ago, you might have learned about even looking like x squared as an example, and it's symmetric to the y-axis, because it looks like that. And the cosine graph, the way I remember it is it starts at 1 and comes on down, repeats, and it's like that. It's symmetric to the origin, symmetric to the y-axis. So their graph is probably a lot better than mine. Now theirs just starts here at 0, so it would continue down and go like that, you know. But that's symmetric to the y-axis. And doesn't say, oh, down here at the very bottom, it says cosine is even, because it's symmetric to the y-axis, and it even tells you that part. Now sine, on the other hand, is odd, and it's symmetric to the origin. So odd was like x cubed, it's symmetric to the origin, and that means it's in like diagonal quadrants. That's the general explanation of it. And for our purposes, when we're talking about sine, it goes through the origin and it matches up here, and then these would match up, and it's symmetric to the origin. Now, in the same way, secant and cosecant would be in this column, and in the same way, tangent also goes through the origin, and it's symmetric to the origin, and cotan is the other way. Cotan would be like that, and then repeat it. Well, maybe, yeah. tan and cotan are not symmetric to the y-axis or the other one. Well, yeah, it is. Just crossed it out. Tangent is symmetric to the origin. This was right. My bad. So tangent in a limited domain, which is what I was wondering about, whether it is or not. In a limited domain, it is. Let me just take you through my quick thought process. I was thinking, well, no, it's not, because it repeats so many times. But actually, yes, it is, because that matches up. That does. That one, and so forth. So it actually does. And then if I just change this one to be cotan, then you can see this top part corresponds to this bottom part. Okay. That doesn't look symmetric to the y-axis at all, and so that's not even. So I guess watch out if you get cotan, because that's definitely not symmetric to either one. Cotangent is not symmetric to the origin or the y-axis. Tangent is symmetric to the origin. Okay, looks like that'll do it for this video. Hope that helps.